In this video, we will review the idea of antiderivatives. By definition, a function capital F is an antiderivative of a function lowercase f on an interval I if f prime of x, capital F prime of x, is equal to lowercase f of x for all x in the interval I. In other words, capital F is an antiderivative for lowercase f if lowercase f is the derivative of capital F. Here's an example. If capital F of x is equal to 2x to the third plus natural log x plus 8, then this is an antiderivative of lowercase f equals 6x squared plus 1 over x on the interval 0 to infinity. Because if I take the derivative of capital F of x, the derivative of 2x to the third is 6x squared. The derivative of natural log x is 1 over x. The derivative of 8 is 0. And that is equal to lowercase f of x. And this is true for all x values in the interval from 0 to infinity. Notice that the constant 8, when I take the derivative, gives me 0. So I could replace this constant 8 by any constant at all. This tells us the theorem that if capital F is an antiderivative of lowercase f on an interval, then the most general antiderivative of lowercase f is capital F of x plus c, where c is an arbitrary constant. So we can add any constant to our antiderivative and still have an antiderivative for the same function. Here's an example. Find the most general antiderivative of the function g of t equals square root of t minus cosecant squared t plus 8. Our notation for an antiderivative typically is we use the capital letter version of the function name. So this function is lowercase g of t. For my antiderivative, I will call it capital G of t. Remember that the square root of t is the same as t to the 1/2 power. The power rule for antiderivatives says that I take my base t, I take the exponent 1/2 and add 1 to get 3/2, and then I divide by the new exponent. Dividing by 3/2 is the same as multiplying by 2/3. Moving on to the next term, I need a function whose derivative is negative cosecant squared of t. I know that the derivative of cotangent of t is negative cosecant squared of t. And for our third term, I need a function whose derivative is 8. I know that the derivative of 8t is 8. So one antiderivative is capital G of t equals 2/3 t to the 3/2 plus cotangent of t plus 8t. To get the most general antiderivative, I tack on this plus c at the end, which is representing any constant, because whatever constant this is, if I take the derivative, we will get 0, and we can always imagine a 0 added to the end of our function. One more example here. Let's find the function f if f prime of x is equal to 3x plus cosine x and f of 0 is equal to 4. So we know that f is an antiderivative of f prime. So if I know that f prime of x is equal to 3x plus cosine x, then f of x is a function whose derivative is 3x plus cosine x. So the antiderivative of 3x is 3/2 x squared, and the antiderivative of cosine x is sine of x. And to get the most general antiderivative, we tack on plus c. Okay, however, f is a particular function. We know that f of 0 must equal 4. So we will use this information to solve for c. This tells us that when x is 0, y is 4, or in other words, f of x is 4. So 4 is equal to 3/2 times 0 squared plus sine of 0 plus c, which means 4 is equal to 0 plus c, because sine of 0 is 0. So c is equal to 4. So overall, our function f of x is 3/2 x squared plus sine of x plus 4. A problem like this, where we know the derivative and we know a particular point on the graph of the function, is called an initial value problem. We will talk a little bit more about this type of problem later in the class.